Yeah, first I would like to thank the organizer for the invitation and also for the selection committee for recognizing our work for this award. Okay, so today I'm going to talk about this. So two parts. One is solving partial differential equations on point clouds. Then we'll see how these tools, its action, okay, which is basically applied to shape registration or shape correspondence. This is joint work with my former postdoc, Rongjie Lai. He will be here next week, give a talk, and my two former students. Okay, so point cloud. I think there's nothing. It's very intuitive. It's very simple, but it's everywhere. So it's the most basic, natural, and ubiquitous representation of geometry and data, especially nowadays. We're talking about data in high dimension. It's very difficult to generate mesh, triangulation, all those things. What you have is just point cloud. So this is if you use a laser scanner for modeling, for example, in this room. It's far harder for, first of all, when you talk anything about geometry, it's much harder than image. You can easily take a picture of this image. Every one of you is in the image, the chairs, everything is pretty clear. That's a projection in 2D. But if you really want to create a 3D model of this room, especially with you, with the chairs, with the detail like your hairs, all those things, it's still a very challenging thing. But a basic information or observation or data is just a bunch of points. Okay. Of course, nowadays we're talking about data science, and most of the time to characterize a human being, you probably need a lot of numbers, a lot of different measurement. So just like an image, if you think of image, this may be 32 by 32, then each image is a point in this 32 by 32 space. Okay, it's in very high dimensions. And this is a point cloud in there, you can think of that. But most likely this is not a random dot in this 32 by 32 space because they're all human faces. So usually they lie on a low dimensional manifold. I think people did some kind of cognitive or other kind of studies, probably around dimension 10. Okay, if you talk about all possible human faces, it's roughly on the 10-dimensional manifold. Okay, so well, you can think this itself is an object, right? A bunch of points, but this representation is quite difficult to use. It's just a collection of discrete and structured data. There's no connection information, no structure information. It's just a bunch of points. Okay, that's the raw data. But how, and there's no like image, you put it on the grid. So the grid is a very natural way to you view the image as a function on a square, for example. And the square is the domain you can easily parameterize or represent an image. And every image is following this data structure. But for this point cloud, there's no such things. No easy, it's not only unstructured, but also no easy parametrization. Okay, even a sphere, you don't have a non-singular global parametrization. Or mesh, 2D, you can do it. It's already quite complicated. 3D, high D is even harder. And also this, your image, your sampling is very uniform on all those pixels. Here, there may be holes, there may be edges, those things. It's quite non-uniform, the sampling. So those are the challenges just in terms of the representation. It's even, as I said, harder to say how you describe a point cloud, right? How you can see something on a higher level about this point cloud rather than just 1,000, 10 millions of points and their coordinates. So how do you give some characterization or some characterized by some structures, okay? So we propose basically using geometric PDE to connect the dots. Okay, so these are the dots, but if you put some geometric PDE on it, actually when you find the solution of the PDE, you do feel the connection between the points because they tell you local geometry and the PDE tell you how local geometry are patched together to provide the solution. So it's really connecting the dots, okay, using geometrical PDEs. Of course, you can think about if we really want to simulate, say, something on Earth, then these things is on the sphere. So that's on the manifold. Connecting the dot and then try to obtain some geometric understanding of this very discrete and structured object. Then we'll see how that's used later. Okay, so let me just highlight a few key features of our method. So no mesh, no parametrization is needed. You just directly do everything on this raw point cloud data. And only local information, because we're solving PDEs, the only thing you need is local information. So only local information, such as you and your k nearest neighbor points are needed. The framework works for manifolds for arbitrary dimensions and or even, like a curve in 3D, that's fine. You have codimension 2. You can have an open with a manifold with boundary, with certain boundary condition, that's fine. And most importantly, the complexity scales with the total number of points, of course. That's how you describe your object. And the intrinsic dimension. Say if you're embedding a curve in 3D, 4D, the computation cost is not going to be proportional to 3D, 4D, but it's just proportional to 1D. Okay, that's the intrinsic dimension of your object. Okay, the idea cannot be simpler. It's basically once you learn first course in calculus, that's enough to understand the basic idea behind this. If we're talking about gradient in the Euclidean space, everybody knows how to do that, partial x, or df dx, so that's how you calculate it. But when you're talking about differentiation on the manifolds, because your function is defined on the manifold, the only thing important when you're taking the derivative is the underlying metric. Nothing more, nothing less. Okay, the underlying metric. So how do you do instead of this rate of change with respect to Euclidean distance? This is rate of change with respect to the underlying metric. Okay, and also you know this, you can define this. That's also the metric you care about. So the key idea is nothing is chain rule. So let's say in 1D, you want to take derivative, the rate of change of function with respect to the arc length, okay, which is if the curve is very curved in Euclidean space, embedded in this Euclidean space, this arc length is very different from Euclidean length. But when you do this rate of change, you can easily change it to rate of change with some underlying coordinates, and how underlying coordinate change with this arc length, and then that is inverse of this. So basically, you only needed to know two things: how this rate of change of your function with respect to this common background coordinate, and how your curve, your manifold, change with respect to the underlying coordinate system. So once you have this, you know this. So, then this is, the thing is, can you find a local coordinate system? As I said, everything is local derivative. Local coordinate system so that your function, originally defined on the manifold, and this manifold are all well-defined functions in that coordinate system. If it is, then you can use polynomial, least square using polynomial to approximate this f, using least square polynomial approximation of the manifold, and all these things are computable. Once computable, this is computable. The basic idea is just that simple. You don't need mesh, you need parametrization, so on. Okay, so as I said, the key point is this can be computed from a local approximation of the manifold M and the function f in this. And the tangent coordinate is a good one, right? Every locally you can linearize that. Your function, your manifold is some kind of locally you can regard it as a well-defined function in this tangential coordinate. So that's all what it says. Okay, we already used this idea in our earlier work, in this work, but it's mainly try to do the moving interface problem. Okay, so this is the picture. So this is the point cloud. Okay, and you use that. You can using local PCA to find the tangential direction, normal direction, and you project this point down to this tangent space, and then this curve becomes a function in terms of this projection of this point. And what this little dots means is a function defined on this curve, which is corresponding to each point. And then this function also becomes a function in this tangent coordinate. So both, this is the function you try to differentiate, is a function in this coordinate, and this curve or this manifold can also be defined as a function in this local coordinate system, and then you can do what I said, chain rule, to compute the derivative of this function with respect to this arc length on this curve. Okay. So if you have a question, please stop me. So I think I'm more than happy to answer your question. Yeah, as I said, the most important thing is in local coordinates, M, F are all well-defined function, and given the points, this actually doing these square things, you'll find this, given this point, differentiation we all know is a linear operator, so that's the same. Even you do least square approximation, you are solving a linear system to find those coefficients, so it's still is a linear function of linear operator or linear function of these values. Once it's nonlinear in this point, of course, that's how the manifold is defined. But once this is given, you define any function that, then it's a linear function, a linear operation of this. Okay, so I don't want to say the formulation is the very standard least square formulation. And you also can, there were some this approximation error estimate. So the basic thing is your error depends on how well you sample the local geometry. If you use a uniform grid, the approximation error is just like you approximate a standard function, you clean the space. Okay. If you don't have that, so some direction you don't have points, of course you're going to make a lot of error in there. But in general, if you assume your sampling is good enough, you know, anything you do is just as good as your data. If your data is bad, you can do nothing about it. But if your data is pretty good, then you can have this error estimate. But there's something more. Actually, we find it out. There are some interesting cancellation property. So what this says, for example, the M is the order of polynomial you use for the approximation. So usually use quadratic. Okay, M is good 2. And plus 1 is 3. And then I want to approximate first derivative, you'll get second order accuracy. But if you want to approximate the second derivative, you only get first order accuracy, so which is not so good. But actually, it's better than that in practice. If your points are pretty sampled pretty well, there's some cancellation. So in a special case, when the derivative you want to approximate and the polynomial you use are the same parity. So for example, I'm using still in quadratic, and I'm approximate the curvature or Laplacian operator, which is second derivative. So then you will say this instead plus 1, you can have some superconvergence. M plus 2 minus 2. 2 plus 2 minus 2, you get second order. Even I only use quadratic approximation locally, when I calculate curvature or Laplacian, it still has second order accuracy. Okay, so this is basically the thing. Okay, any differential operator, you're interested in gradient operator, Laplace operator, or even any other, because you just simply use chain rule. Okay, so you can find it. And we can do this applied to generalize to for example, high dimension doesn't matter, but of course the difficulty is when you do the local reconstruction, your tangent space grow with your dimension. When you're using quadratic to approximate 5, 6 dimensions, the terms are quite a lot. But here I'm trying to say, okay, so say you have a curve in 3D, okay? Then I claim our algorithm is roughly as you really just doing something in 1D. The reason is because when you use PCA, you will find there's only one direction corresponding to the tangent space, two other direction corresponding to the normal space, so which means your normal space and the function you want to approximate is just a function of that tangent space, 1D. So it's still one variable function, so this is how many, what's the true dimension your manifold is, that is here. And all the other, here. And all the other co-dimension is nothing, it's just function of the number of variable function of the dimension that is corresponding to your intrinsic dimension rather than embedding dimension. And you can do this, you can do the many things. Okay, so here we just try to solve some, using our method to solve some problem. This is heat equation on a flat 2 torus in 4D. Okay, so which means it's equivalent to solving a heat equation in 2D. And what I want to say is, you see the order of convergence is 2, because I'm solving heat equation. I only use second order polynomial approximation due to our super convergence theorem. It predicts second order. You see it's second order. And we can see flat 3 torus in this, I see the convergence is still those things. Okay, so this is reaction diffusion equation, nonlinear equation on a sphere. So we can do that. The heat diffuse from a point source on the air, how the heat diffuses. That's basically why I say that the diffusion process actually fuse the geometry and fuse the shape. So that's what we're going to use later on. But this is, and this is exactly what we're going to use later is the eigenvalues and eigenfunctions for a Laplace Beltramian operator. So it's like a Fourier series on a manifold. So first of all, it provides an orthogonal basis to represent any function in L2, and also it has a multi-scale feature. So we're going to use that heavily later on. We also can solve hyperbolic PDEs using some kind of semi-Lagrangian method. And also we can solve somehow using the local reconstruction. Now, if you have boundary, then we can also do local reconstruction of the boundary. Then we can find its normal. If you have a normal direction that is normal to the boundary, you can approximate this as well. So you can solve manifold with a boundary, not just closed manifold, which does not have boundary condition. Yeah, this is some application we did earlier, like construction of conformal mappings. Okay, just directly on point clouds. You try to minimize the mapping from your manifold to a sphere, to sphere, a real sphere, and minimize this energy. And we can do in our way. And you can see this is to check that you preserve the angle, conformal mapping. A grid here, orthogonal grid is mapped to orthogonal grid. Of course, there's area become distorted, but this conformal geometry says all this angle is preserved. Well, there are other things I will skip of this. We also, when you solve, for example, Laplace equation, I think the best still I think the best way to do it using finite element method, because you can use using weak formulation that require your representation or anything is one order less, and you know, your condition number is also bad, but can be worse. So I think finite element is a good way to solve elliptic equations. So by doing local mesh, so we never construct a global mesh. We find k nearest neighbor, we project to the tangent plane like before, and we triangulate that things. And you can just do a local triangulation. And you first ring, second ring, you can do something. So I don't think I want to do the detail here. Yeah, this is, we use, this is, before just using point clouds, here use local mesh to solve the same equation, and actually we can also solve geodesic distance, so which is a Hamilton-Jacobi equation on the manifold, and we have this fast marching method or fast sweeping method to solve it very quickly, and then you can find the geodesics between any 2 points. Okay. Okay, so now the second part, it's I would say it's quite interesting application to shape analysis, as I said. Since we can solve geometrical PDE on point cloud, so which means we have already connect the dots. Now, how to use those information for us to deal with some high-level problems like registration of two shapes. So that's very important in computer vision, because if you want to compare two shapes, yes, yes. Okay, so it's basically we can define. So the main thing about this is you define a basis. So our basis is basically once you triangulate down there. So basically you project your points down there, and you do a local triangulation, and the basis function is 1 at this point and 0 at that polygonal with this at the center. So when you locally look, it's like hexagons. Okay, so and then that's your basis function, and then you need to do is to find the inner product and the stiffness matrix between these bases. The only thing is, when I'm centered, I have a local triangulation, but when I'm talking to a neighbor, it has its own triangulation. There's not guaranteed symmetric, but we do some kind of average between these two ways of doing things. And then, so many things, what my point is, you try to approximate the mass matrix and stiffness matrix defined in that way, the two basis functions there. Yes. Yes, integrating by part, you don't see anything in the discretization. You don't see it's just the standard integration by part on the manifold, because if you have boundary, there's some boundary term. If there's no boundary, just freely integrating by part to reduce to this gradient dot gradient equal to gradient f dot u, something like that. And mathematically, there's no difference in that formulation. But the main thing is how do you calculate, because well, when you do numerical calculation, there's two important things. The first one, how do you choose a basis to represent it? And the basis, I said, is that the basis. And when you solve the weak formulation, you need to find the inner product between this basis you created. And that is something, what I said. You just do this triangulation and do this. It's very similar to Euclidean space. Yeah. Basically, say if 2 points they share the same edge, so there are two. There is a triangle they share. Okay, so yeah. Yeah. So the only Okay, so if I'm talking this point and there's a basis here, there's a basis here. Their interaction is only through these two triangles. So everything, it's just almost like the regular ones. Uh, it's their interaction is through their interaction through these triangles. Yeah. So, but as I said, the only thing is you do here centered at this point. When you center this point, maybe there's other points. So each triangle uh, may not be the same. The only thing is if they somehow share at the different triangle, you have the average on these two triangles. Okay. So the overlap is, so when I centered here, their interaction is through the triangulation from this k nearest neighbor point from this project down triangulation, they interact this. And this may not interact with it when you go to centered at this point, because I only do k nearest neighbor there and do totally new triangulation. There's no guarantee this triangulation is compatible with this. If no compatibility, if there's two, then I will have to do average of this. Yeah. To what? High order. Oh, okay. So very good question. I think if you really want to do it, you can do it in a sense. The only thing is your basis function cannot be piecewise linear. You involve second ring rather than the first ring. You involve in second ring and using some quadratic basis function to do that. Yeah. Whether it's worth it or not, I don't know. Yeah. But this is, the standard finite element things. Yeah. But without the global mesh. Okay, so non-rigid shape matching. So as I said, for example, if you want to compare two shapes, just these two bottles, right? This is identically the same, but they can be embedded in different way. So if you just look at their coordinates, you cannot compare. You have to align them and then compare. Then that's meaningful. So the first thing many times in shape, computer vision shape recognition is you have to do registration to align two shapes together. And then you can do comparing or something like that. But then you have many challenges. One is embedding is non-unique, right? So I think I have a piece of paper here. Okay, if you can give me one. Thank you. Yeah, that's good enough. Yeah, this is a flat piece, right? But you can embed it in this way. You can embed it in this way. You can embed it in different way, but they are all the same shape, right? Essentially, intrinsically, it's a flat piece. So embedding is not unique. There are all kinds of isometric deformation. You can do that. And also shape space is nonlinear, not like images. You can talk about space of images, and then you create a basis for that linear space. You're using that space, using representation, then you do some comparison. So here you don't, a shape space is nonlinear. And addition of two shapes is not, in general, it's not a shape, you just do addition. And no canonical representation parametrization, no uniform sampling. So all this, when you really look at the point clouds laser from a laser pointer, there's some region is shaded from you, so you have a lot of holes, a lot of boundaries. So this is all the challenges. Actually, I think a few years ago at least it was true. You have ImageNet. You have so many good images on the internet, right? But if you look at shape, there's not a very good shape net. There's maybe 1,000, 10,000 at most available on the internet. So just one dimension more, things become much more complicated. So the thing is, for example, what we're trying to do is registration of these two shapes. Okay, so you say this is very different. Look, the embedding is very different. But if you think what I said, this is of course, this is not data driven, this is model driven. So you think unless your skin is, or you do very extreme motions, so your skin is not stretched too much or shrink too much. So most points on your skin will keep their distance along, your body surface when you do the different motions or pose. Okay, so that's the model. So we think a point here, a point here, and a point here, and a point here, their distance. If there's a correspondence, then the geodesic distance between the point here and these two corresponding points here and here, it should be almost the same. Okay, that's the model. Okay, so one way to do that is to take out this variance. There's this isometric deformation, infinite many possible deformation. That's a huge space, but you want to project it out. You really want to find quantities that is invariant under this deformation. So the one thing you can see, the quantity that does not change is the eigenvalues and eigenfunctions for the Laplace spectrometry operator, because it's only depend on the metric. If your underlying metric is not changed, everything is not changed. Okay, so now instead of, this is your real point cloud. Okay, this is your real point cloud. This is your coordinates of point in 3D, so that's x, y, z. But I don't want to use that. That's not intrinsic. As I said, you can have different way of embedding this same shape into this 3D dimension. So I want to use a new coordinate system, which is, okay, remember phi 1, phi 2, phi 3 is the first eigenfunction, non-trivial eigenfunction, second eigenfunction, third eigenfunction, and so on and so forth. So its coordinate at this xi is the value of this eigenfunction at that point. Okay, so that's, I map a point in R3 to maybe, so you will see this could be 200. If I use 200, depending on how much resolution I want to resolve the shape. So this is depend on the noise level. This is something is saying, okay, how much I want to go to the detail. This is where you stop here, it roughly tell you what detail you can see or what noise level you can tolerate. And remember, okay, is phi 1 the value of the eigenfunction at the same point. Okay, why this is good? Because you see how you create, if you sum sine of 2 pi x together, 2 pi kx together for all possible k, what do you get? You're getting closer to a delta function. So you really, I know all the different eigenfunction at this point, roughly I can pinpoint where this point is globally in terms of the global position. So this has global information. It can localize where you are, and it's only depend on metric, doesn't depend on the transformation, isometric transformation, so you don't have that. Okay. So that's that. You find some quantities invariant under the transformation, which I don't want to depend on. Okay, so that's really the good things you have achieved so far. So it's intrinsic global point signature. It's not global positioning system, but it's similar to that. Invariant to isometric transformation, and most importantly, it also has multi-scale nature. Okay, depending on where you stop, basically you see what scale you see of your shape. So for example, give you some example. So okay, this is nothing, just an eigenfunction. This is the first non-trivial eigenfunction, so mainly oscillate in these major directions. And then the second one is changing still in this direction, but the third one is changing in the other direction, and so on and so forth. So you can see this. So you have no way to guess what the eigenfunctions are, but they definitely form a orthonormal basis, has a multi-scale nature in it, just like Fourier series. You can think of this as the Fourier series. And this is saying multi-scale nature. If you reconstruct a shape, okay, there's a shape, only using the first 20 eigenfunctions, you see you lose all the details, okay, but you have the big shape body. And you use more, you see more things, you see more. After you use 200, it's pretty much recover everything in the original shape. So multi-scale nature. And also, you see the most important point is after the transformation, these three in the embedding space, they are very different, right? You have no way to say this is similar to this, but after the transformation, they really look similar. They should be, because this assume you don't have, it's mainly approximately an asymmetric transformation between the different poles. Yeah, here's another example showing, this is the cat, this is dog. In Euclidean space, definitely I would say this is much closer to this one, to the dog in the same pose, rather than the cat to this cat in different pose. Okay, so but when you transform into this spectrum domain, you will see, yeah, indeed, these two cats are more similar than cats versus this dog. But you introduce the good things. I think the most important thing, I still think that's the most important thing in life, is no free lunch. When you gain something, you will lose something. But hopefully, the something you gain is something you're not good at it. Something you lose, you have more handle on it. So that's the trade-off you want to have. But definitely, you gain something, you lose something. In this spectrum, as we know, this is in the eigensystem, there's ambiguity inside. Okay. If you have no simple no non-simple eigenvalues, there is a space, okay, depending on the multiplicity of the eigenvalues. The basis in that space is arbitrary, but importantly, it's a rigid transformation, unitary transformation. Okay. Then there's a possible switch of the eigenvalue. If you have nearby one, there could be switch, so the ordering could interchange. So you can see it here. So the first eigenvalues in this pose and this one, they pretty much nothing changes. There's nothing. It's really, you see they correspond to each other. But the second one, you see there's a sign change. Okay, so this is positive, here's negative, here's positive, here's negative. You see. And here, the third and fourth, because there's some symmetry between two front legs, two rear legs, there's a switch in the eigen function. This one corresponding to this corresponding to that. Okay. So those are the challenges, but as I alluded already, the thing is we have to deal with a unitary transformation to conquer this, which is you have better representation, better understanding, rather than all these possible deformations, which you don't know. So the difficulties it turns into is something, well, actually we can deal with more easily than the original difficult parametrized representation of all these different shape deformation. That's infinite dimension space. Okay, so now what we do. Okay, so I think so all I'm saying here is develop some way to address the challenges we introduced. Okay, so that is still, that's not a trivial challenge or difficulties to overcome. But as many people do, is you do some lifting. Okay, instead of talking about correspondence, which is a permutation matrix, which is very discrete, discontinuous, difficult to deal with, to jump from one permutation to the other permutation. Now we think of the permutation will induce a linear map between functions defined on the shape. Okay, then that becomes linear. Okay, so, but of course your space becomes bigger because you're talking about function space, the mapping between function space defined on these two manifolds. But of course, in practice, we always do truncation. So that truncation is basically related to how many eigenfunctions we're going to use. That's the space. We'll introduce a linear transform between function space spanned by first 100 eigenfunction here and first 100 eigenfunction of the second shape. Okay, we're trying to, because the linear, we're trying to find a matrix, and also because we know these two are nearly isometric, we know the matrix can be approximated well by a unitary matrix. Okay, once you have unitary matrix, okay, and you learn linear algebra, that become a projection problem. Okay, L2 projection, because it preserves the distance and all the things. So, okay, so that's basically the things. I won't talk about much detail because it's time limits, and also I think it's a little bit technical. But again, as I said, there are two things. If there's a correspondence, if there is a correspondence, which is a permutation matrix, that will induce a linear map between functions in the function space. And here, the function space has a nice basis. What this matrix is all the eigenfunctions. Okay? So this is eigenfunction, which is the basis for the function space. Here are the eigenfunctions. So I want to find, okay, this C embedded that ambiguity. Okay, we're trying to find the C. But you can say, okay, this is chicken and egg. I want to find the correspondence, but you said you tell me the correspondence, I can find overcome the ambiguity, and with the ambiguity resolved, I can do the correspondence. But this is like a chicken and egg problem. Correspondence and ambiguity in the mapping, they are kind of depend on each other. But we want to do some iterative way, so you have to start with something. So many times, if you give two shapes, people usually give you a few landmarks. Okay, this point should go there, maybe I should go to I, nose should go nose, and something, and then that's where you're starting from. You have a few correspondence, then you want to construct C, and given a C that's overcome, well, not overcome totally, but give a better, resolve the ambiguity better, and then you can find a better correspondence, and better correspondence resolve to better the C, and so on and so forth. Okay, so that's this iterative process. But it's not easy, okay? The reason is people in the past do not really try to avoid the spectral embedding. The main thing is due to these following challenges. Although it has a very nice multi-scale decomposition, this kind of nature, but high spectrum modes, like high frequency mode, always, you need it to resolve, if you want a very accurate registration, or you want to represent a sharp changing function accurately, you need high frequencies. Otherwise, you cannot approximate well. So you need high frequencies. However, computing the high frequencies, and you have to deal with, if you want to go to 200, you have to deal with 200 dimension. So that mapping will be 200 by 200. It's very costly, and it's also the higher mode is sensitive to noise, stability is an issue. Eventually, people don't want to use this because you want to use high frequency, but high frequency is not stable to use. So, but here, mathematically, we're always saying, okay, there's a multi-scale approach. Let me first start from low core scale. So for example, most of your bodies, like the front, back, legs, all these things are in the low mode. So those things you can use low frequency modes or low eigen modes to align them. Once you align them, you have enough these points, align them, and then that allow you to resolve this ambiguity in higher dimension. I can use involving more mode. So there's the cost to fine scale marching. Okay, this is we already proposed some years ago, and there's other people, the computer science people there also did this a little bit later. But there's still, in this previous approach, there's two difficulties. One is, in the old days, all pairs, okay, so we use, say, 10 mode to do the correspondence. Then you know these points on the front and the big smooth part of the body, they align pretty well. But those points on the fingers, on the tips, or on the toes are not aligned well. But when we do this overcoming using this correspondence to find these uh, linear mapping between functions, all these pairs are used. Bad guys, good guys are all used. So that creates a problem because if initially you have too many bad guys, then you will fail. And also because you have average between bad guy and good guys, your convergence is slow. So the thing is, can you select using some criteria to find out what are the good guys, what are the bad guys, and only use the good guys? Iterative method is always it's a very important step is how to use the correct information more than using the wrong information, because iteration means the beginning you have wrong information, right information, you have to filter them out. How do you do that? Okay, and also before we match, just with sign match from using 5 eigenvectors, eigenfunction to 10, 15, you give this jump. It's not data adaptive, because for easy shape, maybe you can from 2 dimensions directly to 10, 10 already you can go to 20. Very fast things. It should be data driven. So we're in our recent work, we're overcoming this too. So one thing is to use where the dual iterative refinement, where the dual come from. So the eigenmode or the spectrum domain is global because Fourier eigenfunction are global information. Here we're going to propose some local information to help you. So dual is local and global. Okay, so in terms of in the physical space. So what we do is if I map to here and my neighbors up to the other things, I just look locally what's the distortion. If the distortion is large, I think the pairing is not good. If the local distortion is small, that's a filtering saying, okay, this could potentially be a good guy. So using this to select not all pairs, but all the pairs that have small local distortion. So that's really filter out many bad points. Maybe there's still a few bad points there, but for example, if I map this point to here, to the wrong hand, but locally they look same. So the local distortion cannot tell whether I map here to here or map here to here. So you cannot, but most of the points, bad points, you can filter out. So that's the first step. The second step is once I know all the good pairings, I want to say what dimension this point, right? PCA, what is telling you is say, you give me a bunch of point clouds, I can say the linear space where all this stay close to. Because of that is a little bit variation that could be noise. If you want to do anything orthogonal to those space, it's not going to be stable and accurate. So we want using the good pair we already have, and also using some of correlation matrix to find out whether it's going to be can support 20 eigenmode, 30 eigenmode, or 41 eigenmode. We use this data tell us where from here, how many dimensions or what scale I can go next. So that's the two major things do. So as I said, this is exactly the algorithm. Each step is quite simple, and you can do it. All those steps I mentioned already. So this is SVD. And also because we restrict our mapping is unitary, finding alignment of 2 point clouds, find the best rigid motion to move these point clouds to here with given correspondence is just the PCA, just as SVD process projection. So it's very easy. So this is our computation cost. Okay, so each step. So now, if you really do these things, the one challenge is you have to compete with the state-of-art algorithm computer scientist design. That's not easy. This guy may not be mathematically sophisticated, but they can optimize almost everything else. So to compute that, it's not an easy job. But this is a few years ago compared to then the state of the art. This is our curve. It's quite better than this, and this is our. this is also saying it's very interesting is that you have to start with a few landmark points. Okay, so you register this to all the other shapes. Okay, this is all other shapes. We start with 4 landmarks, 40 landmarks, 400 landmarks. Eventually, on 4, they all converge to about the same thing. So it's a very robust iterative process. The main reason is because we only select the good pairs. We have a local criterion to select which are already good, which are bad, not using the bad guy, only using the good guy. So it's very robust and it goes very fast from scale to scale. And even, this is very hard because there's artificial boundaries, all these things, and there's you just give part of the body. You want to make the correspondence. Okay, now the whole shape. Then here you cannot use Laplace the eigenvector for this because it's affected by holes, by the boundaries. Here we use global geodesic distance as a global. As I said, the due always means some local criteria, some global criteria. Okay, so here is this. And this is more challenging. There's holes, there's a lot of things. It's definitely not easy. And there's even not the model is not very good. This is not isometric when you have this shape. But we can do a pretty good job, but not a very good job because the model is not correct. Okay, here's the conclusion. So first of all, we developed some way to solve geometric PDEs. That could be used for simulation physical problem, other problem. But the main idea is using simple chain rules. And you don't need a mesh, you don't need parametrization, and flexible and scale well with the intrinsic dimension of the underlying manifold, not embedding dimension. Embedding is non-unique, could be highly redundant, so on and so forth. And by using the geometrical PDEs, we can connect the dots and extract geometric structures information and use that to do some shape analysis, shape correspondence application. Yes, that's it. Mm.
Is this an assumption, or is somehow computationally determined? For example, you have 1 point, then the 10 point closest to it are on the same surface.
No, this is well, computationally you don't need that. You can do this because this is you collect the 10 years neighbor, you do the PCA through the local PCA, you know whether it's has a tangent space. Basically, if you have sudden drop of the eigenvalues, then you know the intrinsic dimension is the leading ones, and there you have to set our thresholding. But this is all the analysis of the assumption is this, but when you do computation, you don't need that. It's true, but you can always do this.
So there are some criteria you can check during the computation.
Yeah, this is totally depends on the computation. Once you have the k-nearest neighbor, you do the PCA, you can say there's a locally there's a lower dimensional structure. If it's nearly identity matrix, means you're just a uniform isotropic point cloud. There's no geometric structure, underlying geometric structure there.
And also, when you say the cat and dog plot, and you say, well, could you explain what we're looking at? You say, like after could you go back to your slides? Like,
where?
Which the cat and dog, you have two like 8 figures on top and then 4 figures on top. So, oh yeah, this one and the next one. So what are we looking at? The next one, the previous one. Yeah, this, like what are the bottom plots?
Oh, okay. Sorry, I didn't say. So these 3 dimensions. So I basically every point, I only use the value of the first 3 eigenfunctions to plot this. It's like eigen decomposition. So basically, that's also what PC is doing, right? Anything just using the first 3 projection to the 3 coordinates to do this. Okay. Yeah.
And also, sorry. So in your original space, there is information whether 2 points are close to each other, and how is this information reflected in the spectrum?
Can you say that again?
For example, you have 2 points. You know these 2 points are very close to each other, and that's the information in the top space. But how do you know that they are still close after you do the solve the Laplacian and look at the spectrum?
Oh, okay. So it's basically see, a point here. Okay, it has a physical coordinate x, y, z, but every point there is embedded into, say, 30 dimension, which is in that dimension is the value of this first 30 eigenfunction at this point. So it's embedded into the spectrum domain. Okay, then I want to find just using the spectral coordinate, in some sense, to using spectral coordinate to find what are the two closest points. So which means a point here after the spectrum embedding is here, so a point here, they should be very close to each other.
So you're somehow confident that two points with the same spectrum should be close to each other.
Yeah, basically, because that's, as I said, if you're talking about, right, you have two lines, you do the Fourier, your eigenfunction of the Fourier just the sine functions, and you look at the sine pi x, 2 pi x, 3 pi x, all the value at this x, and you look at another point there, if they all look the same, they're roughly on the same location in this interval.
Okay, thank you.
Yeah.
Thank you for the nice talk. So, actually, thought about this kind of question, which is recently has been proposed that Fourier analysis has been very useful in developing neural network methods for solving equations. So, spectral embedding is really a natural generalization of the Fourier methods for the equations of manifolds. Do you think that this can have some neural network applications?
Yeah, maybe I address the first part of this first. That should be the same. Once the only difference is in Euclidean domain, your Fourier series is already pre-given. You already know it. Here you have to calculate. When you change the manifold, the eigenfunction different. So this pre-process, you have to pay for the price. Other than that, it's about the same. But I would say if you use, say people already use, the thing is, if you're really doing in high dimension, how do you do Fourier transform in high dimension, 100 dimension? I don't know how you do it, right? You cannot do it cheaply. So I don't think that's a good basis to describe time function in high dimension. But in low dimension, why do I need it? I can easily do Fourier transform, easily. Why do I use a network as a representation? So to me, the Fourier basis, people use that to solve, maybe, okay, there's another way of saying, okay, maybe in Fourier domain, right, my function, okay, functions, everything has dual phase. How you represent it in physical space, how you represent it in Fourier domain. The half function is good in Fourier domain. Then if you're talking about function there, of course, after the transformation, you get some payoff. You really can do something. But I do not see if in low dimension, why do you need the other things to help you? Because most of things already it's very sparse represented, or very few terms is good enough, then all the traditional methods should work well. But if you high dimension, the question is the transformation. Do you have fast algorithms to do it? This is 3-dimensional. Yeah. If you do high dimension, this is graph Laplacian. This graph, you can do similar things like this on the graph Laplacian. But we tried that. It's not easy because in this geometry, you suppose only connected to your neighbors, maybe 6 neighbors, degree only 6. But if your graph, this could be dense graph, then that matrix C has a lot of degree freedom. You don't have enough. We try to apply this to graph. It works here is manifold, so which means related to what the first question, you only directly connected to 6 neighbors. That's probably good enough. So your degree from each point, this, although you have a bunch of points. But in graph, the connection could be much more than this. And then the eigenvalue, eigenfunction ambiguity could be much more complicated. Whether you have enough data, as I said, the chicken and egg, right? The correspondence and this, how do you, in this case, that C has very few degree of freedom. So you utilize that because you assume it's a manifold. On a graph, that C can be as complicated as you want. So you go to dimension n problem, you go to dimension n square problem, and that n square problem has no compression. There's no simpler form. So that's very difficult to do. It's not enough to determine that C, because that's, here the C is unitary, not only unitary, but also because of this, basically in graph there could be the multiplicity could huge. Then there's no way. Here is because your symmetry is very limited, and the things is most of it are simple eigenvalues. That's the multiplicity could be huge. That's really much harder because 5's multiplicity introduce a matrix 25, 5 times 5 to map these two things. So you have no way to do that.